Hello everyone, I'm Nariman.
I'm Moshumi. We are from Auburn University and we are presenting our research on phenotyping of pine tree architecture with stereo vision and deep learning. Other co-authors of this work are Dr. Ian Bao, Rafael Bides, Dr. Kate Pine, and Zingi Zheng. Loblolly pine is the leading timber species in the United States and it has traits such as simple, fast regeneration and rapid growth. Tree breeding programs have focused on selecting families based on traits such as stem volume and straightness. Architectural traits of a pine tree impact its potential value in the timber processing business. Straight trunks can be cut into longer boards. In addition, lower branch angles increase the strength of a stand. The lumber industry routinely buys and sells logs and standing trees based on an estimate of the quantity of board feet they contain. Taper tables are typically constructed using DBH and height as table entries. Visual grading by expert eyes is the current standard for identifying the morphology of pine tree stems and branches, but it is inconsistent and time consuming.
To solve the aforementioned problems, an automated scheme is desired. Some digital approaches for planning a plant structure have been developed, generally based on sonic or electromagnetic principles. These strategies are impractical for wider area since they are difficult to implement and take a long time to use. Recently, terrestrial laser scanners were utilized to reconstruct the architecture of trees. Even though they can properly reconstruct tree architectures, they are very expensive and generate a large quantity of data that must be processed. So we can say that there is no tool that has all the characteristics that we want in one place, such as being low cost, user friendly, and automated. To have an automated system that is easy to use and also cost effective, we can say that the artificial intelligence and computational power that we have nowadays, alongside with the development of algorithms such as instance mass segmentation using deep learning methods, have enabled us to detect objects in an image, which was very challenging even a few years ago. Also, using stereo cameras, we can have cheaper and with higher spatial resolution images by which 3D stereo reconstruction and point cloud analysis is now achievable. The specific research objectives here are to evaluate the feasibility of segmentation of individual pine tree trunks and branches in RGB images using deep learning, and two, to evaluate the potential performance of branch and trunk diameter estimation method that we introduce using mask-based stereo 3D reconstruction and point cloud processing.
As part of our dataset development, 10 loblolly pine trees were randomly picked in a progeny test at a commercial nursery in Georgia. Each tree is divided into 6 sections. In each section, 3 branches are chosen at random and labeled with color-coded tabs. To record stereo videos of individual trees, a portable Z2 stereo camera was used. 4 videos were collected from 4 different viewpoints around the tree. Trunk diameter was measured manually with a tap and labeled with a color tap every meter up to 5 meters. 3 branches were chosen at random and labeled with color coded tabs in each 1 meter segment, beginning with the second part and finishing with the sixth section. A digital protractor was used to measure the angles of the chosen branches. We utilized mass CNN for instance segmentation in our study, which is currently state of the art for instance segmentation. Mass CNN contains an additional branch for predicting segmentation mass for each region of interest and provides 3 outputs for a candidate image, a class label, a bounding box, and the object mask. We utilized Detecton2, a PyTorch-based modular object detection library provided by Facebook AI Research. Detecton2 includes a model zoo with pre-trained models based on the Maskar CNN benchmark COCO dataset. With our Pine Tree dataset, we fine-tuned a COCO pre-trained R50 FPN Maskar CNN model. The hyperparameters used for training are shown in the table. The computer vision annotation tool was used to annotate trunk and branch polygons on 60 images chosen at random from the video frames and then augmented to generate 600 images. Finally, 500 and 100 of the augmented images were chosen at random for training and testing. There were 670 trunk polygons and 3,583 branch polygons in the entire dataset.
We were interested in finding disparity maps for our data set. In the images, trunks were typically larger and had a richer texture for stereo matching. Thus, a semi-global stereo matching algorithm was utilized to generate a dense disparity map for each trunk to reconstruct a 3D stereo image. This stereo matching was found to perform poorly on branches due to their lack of texture, relatively smaller sizes, and occlusion. Thus, another method was used to reconstruct a 3D point cloud for the branches. This approach begins with the template matching utilizing image based of each branch mask. The ideal integer disparity for value for each bounding box was then determined by maximizing the normalized cross-correlation image similarity metric. Only the region near the base of each branch mask was used. The implicit assumption that pixels within the support region have constant disparity does not hold for the branches. So a patch match-based stereo matching algorithm was adopted to find the potentially varying disparity values within a branch mask under a planar constraint. And this enables us to generate a disparity map faster by assuming that all of the branch pixels are located on the same surface. After finding the best plane parameters using patch match algorithm, to find the branch angles, the pixels of the branches and the trunk in a stereo image pair were projected back into the 3D space using the stereo camera parameters such as focal length. And a 3D point cloud for the branches and the trunk was created with respect to the derived disparities from the algorithm. Subsequently, principal component analysis was performed on the 3D point cloud of each branch, and the major axis was considered as the orientation. Using the unit vectors, the angle is measured by the shown formula. To find the trunk diameter, a place on the trunk's edge near the tagging tape was chosen. Then from that location, a line perpendicular to that trunk was explored to discover another spot on the opposite border of the trunk. The corresponding position in the 3D space of the above 2 points were determined using that disparity values were equal to the average disparity value along the line established. The Euclidean distance between the two edge points was used to calculate the trunk diameter.
Figure shows the qualitative instance segmentation results of the Mascar-CNN method in detecting and segmenting branches and trunks in our dataset. The bounding boxes and segmentation masks over the detected objects are both displayed. In the majority of the images in our dataset, the trunks were spotted entirely. Since the dataset was very small, some of the branches were not selected. Average precision 50, 75, small, medium, and large were the evaluation metrics used for the instance segmentation task, and the results are shown in top table. The bounding box detection and segmentation tasks are comparable for AP, AP50, and AP75. But when the area expands, the AP scores for segmentation improves. For APS, APM, and APL, the values are 21.39, 7.83, and 13.54 respectively. In bottom table, it can be seen that the average precision score is better for segmentation compared to bounding box for trunks, and it is the opposite for branches.
The image derived branch angles was found moderately correlated with the manual measurements, with R-square of 66%. MAPE here is 13.2%, and RMSE is 9.5 degrees. The underestimation of branch angle could be explained by one, that is, some branch masks were not linear in shape, and that this caused the PCA algorithm to find an orientation that makes a different angle. And the second reason is that sometimes the patch match stereo matching algorithm failed to find the optimal plane for slanted branches due to the poor image resolution and quality when the branches were small in size or far from the camera. The correlation between the ground truth and image-derived values for trunk diameter shown in the figure is relatively strong, with R-square of 78%. In addition, the table shows that the RMSE and MAPE are 0.033 meters and 9.9% respectively. The reason that the fitted line that to the result of this step underestimate the measured value and the is the assumption that of an equal disparity for both points in the distance between them was calculated. This can be improved by increasing the resolution of the camera, moving it closer to the object, and also having better lighting conditions. All in all, the feasibility of measuring trunk diameter and branch angles of individual loblolly pine tree using a combination of deep learning-based SNES segmentation, stereo 3D reconstruction, and point cloud analysis was assessed. Despite the need for further improvement, the proposed machine vision system has a promising potential and as a high throughput precision phenotyping tool for tree architecture characterization of loblolly pine. This method provides quantitative data compared to visual grading, and thus it can be accelerated tree breeding procedure, resulting in facilitating the selection of tree architecture that is highly productive. This project was supported by the Alabama Agricultural Experiment Station and a Hatch program of National Institute of Food and Agriculture, U.S. Department of Agriculture. And also this project was in collaboration with the cooperative tree improvement program of the North Carolina State University. These are our references, and thank you for your time.